Hey everyone, today I'm going to be showing you how to set up a geometry shader in the Universal Render Pipeline, or URP. And as a bonus, I'm going to show you a trick for setting up code-driven shaders in URP without needing to understand the ins and outs of how to make a code shader in that pipeline. I'm Game Dev Bill. Let's get started. I'm not wearing any glasses. Where'd I put my glasses? This video is a little more technical than most of the ones I've been making. I'm going to try to keep it fairly high level. For more details or to copy paste some code, there will be a link to a specific article tied to this video in the description below. That article will be over at gamedevbill.com. As a quick refresher, there's a lot of stages to the graphics pipeline, and the two you're probably most familiar with are the vertex shader and the fragment shader. 99% of the time if you're writing a shader, it's one of those two. Well, there's a shader stage in between those two. After the vertex function but before the fragment function, there's a method that's called the geometry shader, where the vertex function is run on every vertice, and the fragment shader is run on every fragment or every pixel on the screen. The geometry shader is run on every triangle. So if you had a quad, the vertex shader would be run 4 times, one for each corner, and the geometry shader would be run 2 times because there's 2 triangles in the quad. There's 2 main reasons you would use a geometry shader. One is that you want to have one vertex aware of other vertices and do some calculations. That's actually what I'm going to show today, but today I'm going to keep things really simple as far as actually making a demo of geometry shaders. The more common usage, which will be for a future tutorial, is that a geometry shader, while it takes one triangle in, can put as many triangles out as it wants. You can have a flat plane, for example, that generates a bunch of new triangles to make grass. So if there's specific things that you'd like to see, specific demos of a geometry shader that you want to see in a future tutorial, please let me know in the comments below. For those of you already familiar with URP, you may realize that code shaders are kind of a pain, and shader graphs works really well, but you've probably never noticed anything about geometry in there. Well, shader graph does not support geometry shaders, and code shaders starting from scratch are a bit complicated to set up, but there's one trick I'm going to show you today. You can actually take a shader graph and generate a code shader off of it. So what we're going to do is we're going to set up a shader graph doing some of the initial things we want, generate the code shader, and then add the geometry shader in there. All right, so as I said, I need to make a shader graph. I'll create one here, a PBR graph because I want it lit and everything set up that way. And I'm going to go ahead and make a material off of it and assign it to my cube. Now this doesn't do anything yet, but actually at this point I could generate a code shader from this. Just from the master node alone, you get most of the framework you need. But there's a couple things that are going to be missing that I want to go ahead and add. So I'm going to put in a position node and I'm going to set it to object space. Then I tie this into my alpha. By hooking this position node up to the alpha output, it gives me access to some data that I wouldn't otherwise have. You see, when the shader code is generated, the only data that's passed from the vertex function to the fragment function is exactly what that fragment function needs. And by default, it really doesn't need much. But by putting the position, which is normally just a vertex shader property, by putting the position in as an input into the fragment function, that's going to get passed between the two, which means I can intercept it in my geometry shader. I also specifically tie it into alpha or alpha clipping rather than the color or some other fragment shader output. The reason is that there's multiple passes in the shader, and not all passes care about color, but they do care about alpha. So by feeding it into the alpha, I'll ensure that not only is that data passed from the vertex shader to the fragment shader so that I can intercept it, but it's passed that way in every part of the shader. Then I'm going to copy this position node and feed it into the position of my master node. Now, you're probably saying that doesn't actually do anything. It was already taking the position output. Well, it does one thing in our generated code. You see, the way this code is generated, the fragment function and vertex functions that you have access to in that generated code are not actually the full functions. They're sub-functions that the main shader graph generated underlying shader calls. You don't really want to mess with or have access to that underlying one. Well, the sub-function that's in your file, your generated file, that's going to be called, is only generated if shader graph detects that you're doing something with the vertex function. So by adding this node in here, now in my generated code, I'm going to have a vertex method. So at this point, with just these 2 nodes added, it's actually a great point to generate a code file. I'm going to be doing a little bit more in Shader Graph today, but a lot of times, if I just want to work on a code shader, this is a good starting point. It gives me my vertex function, it gives me a fragment function, and in the fragment function, it gives me access to what I need. The geometry shader I want to make is a simple example where I take in data where the normals are wrong and then fix them in the geometry shader. So to do that, in my vertex shader, I'm going to make the normals wrong. And an easy example of that is I take a cube, balloon out the vertices so that it becomes a sphere. In Shader Graph, I'm going to move this position out a little bit. I'm going to wire this position into an add where I add or subtract 0.5. This makes it so that the center of the cube is mathematically 0, 0. And then I normalize that output and drive that back into another add to move it back into position. And this essentially makes it so that every vertex is exactly 1 unit from the center. Just so you can see what it looks like, I'm going to take the original version and the modified version and feed them into a lerp. I'm going to set up a time node with sine time, offset it so that it's going from 0 to 1 back and forth, and feed that into the time part of the lerp. This is just to show you what exactly this shader is doing. As you can see, I'm moving the vertices from their normal cube-like positioning out into a sphere. One thing to clarify is this only works because my cube is set up to have a very tessellated surface to it. I do that through ProBuilder. You can do a subdivide face. Going back to the shaded version, you can see that the lighting still looks cube-like even when it becomes a sphere. That lerp was just to show you what's going on so you can understand what the shader is doing, but I'm going to delete it before I generate the code. To generate the code file, you then just right-click on the master node and select Show Generated Code. This might open the code up for you in your IDE, or it might not. For me, it opens it up in Writer automatically. Either way, we're not going to actually use the generated file. You need to find the file. It's in your temp folder within the project. So instead of going to project assets, go to project temp. Find the file there, copy it into assets somewhere and rename it. I'm going to name mine geo from graph. Once I've renamed the file, I'm going to go ahead and generate a material for it and assign that material to my cube. Let's open up the shader and take a look. Again, I'm going to keep things relatively high level. There's more details on my website, but we'll just hit on the key points here. So first off, the first line says Shader PBR master. It'll always be named PBR master, and we want to rename it probably to whatever the file name was. Then going down, looking at other parts of the file, there's a pass. There's actually 5 passes in the shader. You don't really need to worry about them. The first one's universal forward, the second one's shadowcaster, the rest are others. It doesn't really matter what's going on here. The main thing is that you just have to know they're there and be aware of it. Moving down through this first pass, there's a bunch of stuff we can ignore, but the first thing I want to pay attention to is where it says pragma vertex vert. Just below that line is where we're going to add pragma geometry geom. And what that's saying is for the geometry stage, run a function called geom. And I have to add that to every single pass in this shader. Going down, I'm going to show you a couple other key parts of this shader file, just in case you're curious. There's a vertex description function. This is essentially what you get for a vertex function. And there's also a surface description function. This is your fragment shader. I'm not going to do any actual logic in this surface description function, but I do need to fix one thing. In my shader graph, I had used position to feed into the alpha. I don't actually want that. It's not actually going to hurt anything here, but I like to go ahead and fix that to say surface.alpha equals 1. We'll have to do that in all of the passes as well. Now, going on beyond this surface method, there's a couple more things to ignore, and then there's the varyings. This is where the magic happens. This is what passes data between the vertex function and the fragment function. It does this by putting the data into registers. So there's a lot here. It's a little bit confusing because there's several layers of indirection going on here. But essentially we can look, and here's a varyings method. This is what actually has the names of the things that are being passed around, but it's going to pack them into registers. So if you look at the packed varyings, you can see that it has all the registers listed, like text chord 0, but it has them with confusing names like interp00. So then there's another method below that called pack varyings, and that's what actually connects the dots and ties named variables into registers. It's a little hard to keep up with, but we're going to decode it and put in a layer in the geometry shader that extracts the data we want. With that quick overview, now it's time to actually write our geometry code. we're not going to add it inside the passes. I'm going to instead add it outside as an include that all the passes can reference. That way I only have to write the method once. So up at the very top, right inside the subshader, I add HLSL include. This again means I'm going to put some methods in here, some data in here that can be included with all the other passes. Step 1 is just to define our skeleton. So I'm going to make a struct called geomData. This is the data that I'm going to use in my geometry method. Next, I'll set up the basic frame of the geometry method. I'm naming it geom. This is important. This has to match what we typed in earlier where we said pragma geometry geom. That method name has to match. What it's going to take in is a triangle, which is an array of 3 geom datas. And then what it's going to return is a triangle stream. This is set up this way so that we can return 3 or 6 or 9 or however many vertices we need. The key is you have to tell the compiler how many you're going to return at a maximum. And that's what this line is just before the geom function, max vertex count 3. So for now, I'm just going to return the 3 that I get in. Let's fill in this geom data. So the way I'm going to do this is I'm actually copying things from the varying methods down below. First off, I'm going to copy from packed varyings. This is what gives me the registers that are being used and ties them to the weird auto-generated names. Then if I reference that varying below, I can figure out which variable is passed into which register, and then I can just rename my variables to match. With that data in place, I'm now going to set up a geometry shader that does nothing. It'll just take in the input data and pass it back out. To start, I make a geomData vert0 and copy the input 0 from that. Then do that 2 more times for vert1 and vert2. Then I take my copied geomData and feed that into the try stream. Lastly, I have to say trystream.restartStrip. This is what tells the stream that I've finished that triangle. So every time you put 3 vertices in, you have to say restart strip right afterwards. With that, I have the basic do-nothing geometry shader. It's functional in URP. We didn't have to do a lot of coding to get there. And now you can do all sorts of things with geometry shaders. Jumping back into the Unity editor, I can verify that I didn't break anything. Things are working. The code shader is doing what it was doing before, but now it's doing it through a geometry shader. So let's get in and actually fix our normals. As a reminder, to calculate a normal, you just need the 2 vertices. So we've got a triangle in that geometry shader. We just need to figure out the lines that represent 2 sides of that triangle, and then we can use the cross product to calculate the normal. Going back into the geometry function, I'm going to make a float3 normal. And this is going to be, as I said, the cross product of 2 lines. I'm going to go ahead and normalize the output of that cross product because I always like to normalize things whenever in doubt. If I'm messing with normals, always normalize. So the 2 lines I need to put in are 2 sides of the triangle. So to get sides from vertices, you take one of the vertices position and subtract another one. You'll notice that I'm using position WS. This is the world space position. I only have access to this because of that thing I did way back at the beginning where I tied the position into the alpha. If you remember that, if I hadn't done that, then the only position I'd have access to at this point would be the clip space position, which doesn't actually give us the information we want. Working with the world space positions makes things much easier. We can calculate a normal. Once I have that calculated, I just set that into the normals on each vert, and my work is done. Going back into the editor, you can see that the normals actually look correct now. They look like a sphere should. As you can see each triangle in the shape, and that's because for every triangle we calculated a single normal, and things aren't being smoothed. That's okay because this tutorial isn't really about fixing normals, it's about how to set up a geometry shader. This just happened to be a convenient example. Just so you can better see what it looks like, I do have a version of this where I kept the vertex function to have that lerp in it. And if I turn that back on, you can see this changing from a cube to a sphere, and you can see the normals correctly reacting to the light. As I said at the beginning, geometry shaders are most often used to generate more geometry. But there's all sorts of things you can do with geometry shaders. Here I've got an example where I'm taking each triangle, duplicating it a bunch of times, giving it different colors, having them all move around and reassemble themselves into a shape that I've named Velma. Here's an example where I've taken a sphere and I have generated a little arrow that points out along the normals. This is useful if you're running into problems with normals. Again, there's so much more I could dig into. Geometry shaders have so much potential. If there's something specific you want to see, let me know in the comments. Please subscribe. Thank you all for watching. It's really been great.